Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss problems on bus and memory transfers. So, the computer, it can be used to perform various operations, and it can be defined as the computer is an electronic device that can be programmed to accept the data, process it, and generate the results to the user. So in a computer, we have several modules. So all these different modules are interconnected through the buses. So bus means physically a set of wires. So physically a set of wires that can be used to transfer the information from one module to the another module. So bus means physically a set of wires. So these components, the components of the computer are connected to these buses. So here you can see the basic computer organization. So mainly the basic computer, it has three functional parts that are CPU, memory subsystem, IO subsystem. That includes both input devices as well as the output devices. So in addition to that, again the CPU, it is having various modules that are ALU, arithmetic and logic unit, control unit, and some internal registers. So in order to transfer, exchange the information between them, it requires physically a set of wires. So physically a set of wires is nothing but a buses. Okay, so mainly we have different buses in the computer. So mainly we have three types of buses. One is the address bus, data bus, and the control bus. So these are the three types. So based on the type of the information they carry, the buses are classified into these three types. First one is the address bus. Address bus means a set of wires that can be used to carry the address information. That is the address bus. Next one, data bus. So a set of wires that can be used to carry the data information. That is a data bus. And control bus. So the control bus, a set of wires that can be used to carry the control information like some read, write, reset, clear. So these are where the various control signals. So these control signals are carried by the set of wires that is called control bus. So all these buses are connected from one module to the another module for exchange of the information. So as the complexity of the computer system increases, it becomes more efficient at using buses rather than the direct connections between every pair of the devices. So as the complexity of the computer system increases, so it is efficient for using the buses rather than the direct connections, because if we made a direct connections between the various modules, we require a lot of connecting wires, and also the size and the complexity of the system also increases. So to overcome the drawbacks faced by using the direct connections between the devices, we are using a efficient method that is called buses. So by using these buses, we can reduce the complexity, cost, and also we can improve the performance, because by using buses, it can consume less amount of power. Okay, so these are the advantages with using the buses. So using buses is a, it is an efficient way. So let's see how these various modules are connected using this buses. So we have a CPU, memory subsystem, IO subsystem. So these are the three essential parts of the computer. So all these modules are connected through the various buses. So already just before in the previous slide, we have seen the types of buses. We have mainly three types of buses: address bus, data bus, and the control bus. So the address bus is a unidirectional, that is from CPU to the memory, and data bus it is a bidirectional, because we need to transfer the information from the CPU to the memory subsystem and memory subsystem to the CPU. Similarly, we can also transfer the data from and to the IO device. So that's why the data bus is a bidirectional. On the control bus, so control bus also it is a bidirectional bus. So that means the control signals can be transferred from the CPU to the memory or from memory to the CPU. Okay. So these IO devices. So every IO device having three buses. So these buses are connected to the respective system buses. So the address bus of the IO device is connected to the address bus of the system CPU. Similarly, the data bus of the IO device is connected to the data bus of the CPU. Similarly, the control bus of the IO device is connected to the control bus of the CPU. So like that, all various IO devices are connected to the CPU. So if the CPU wants to access any IO device, it can access through using some address, because every IO device is having some unique address. So using that unique address, the CPU will access that particular IO device. Suppose if the IO device address is 70H, H means hexadecimal. So because the addresses will be mentioned in the hexadecimal representation. So suppose if the CPU wants to access the device with 70 as address, so that address information will be sent through this address bus to the IO device. So if the address generated by the CPU is matched with the address of the IO device, then that particular IO device will be connected to the CPU so that it can access the data. So in this way, the CPU can access any IO device using that particular unique address. So we will solve some problems on these buses and memory transfer. So first question is, how many 128 by 8 RAM chips are needed to provide a memory capacity of 2048 bytes? And second one is, how many lines of address bus must be used to access 2048 bytes of memory? How many of these lines will be common to all chips? And the third CBT is, how many lines must be decoded for the chip selector, specify the size of the decoder. So we have to read the problem once or twice, because for understanding purpose. So first we need to understand the problem clearly. Then we have to solve it. So first one is, how many 128 by 8 RAM chips are needed to provide a memory capacity of 2048 bytes. So we have a 128 by 8 RAM chips. So using that chips, we have to provide a memory capacity of 2048 bytes. So let's see how we can solve this. So according to the question, we have 128 by 8 RAM chips. So 128 into 8 bits. So that means total this particular chip it contains 1024 bits. So 1024. So if we convert that 1024 bits into bytes, so that means we have to divide the 1024 bits with 8, so that we will get the size in bytes. So if you divide that 1024 by 8, we will get 128 bytes. 128 bytes. So one RAM chip it can provide 128 bytes. So like that, the number of chips required to provide a memory space of 2048 bytes. So that means we have to divide the 2048 by 128. So that means one RAM chip provides 128 bytes. So each chip is a 128 multiplied with the number of chips. That is equal to 2048 2048 because all the values are in the bytes. So n is equal to 2048 by 128. So it results 16. That means total we require 16 bits to provide memory size of 2048 bytes. Next one, how many lines of address bus must be used to access 2048 bytes of memory? How many of these lines will be common to all chips? So how many lines of address bus must be used to access 2048 bytes? So in order to access 2048 bytes, the number of address bus or number of address lines are required. Okay, so 2048 locations. So 2048 locations are there. Okay, so same address lines as 1 8 bits for representing 2048. So that means with the 10 lines, so with the 10 address lines, we can represent up to 1024 memory locations. So with 11 address lines, 2048. So that means we require 11 address lines in order to represent the 2048 memory locations. So 11 lines of address bus is required. Okay. And the second one is how many of these lines will be common to all chips? How many lines will be common to all chips? Because the size of the every chip is 128 by 8. So this is a chip. So 128 is a 128 bytes, 128 bytes. Okay, and 8. So that means we have total we have 128 memory locations, and each memory location we can store 8 bits of data. So that is a size of the capacity. Okay, so that means 120, in order to represent the 128 memory locations, we require 7 address lines. So we require 7 address lines so that we can access all these 128 memory locations. Okay, so total 7 address lines will be the common for all the chips. How many lines must be decoded for the chip selector? Specify the size of the decoder. So the 4 address lines must be decoded to select the right chip. Because see, so total we have 16 chips, 16 RAM chips, 16 128 by 8 RAM chips. Okay. So in order to decode, we require the 4 by 16, 4 by 16 decoder so that we can access all those 16 RAM chips. Because here the inputs are 4 and outputs are 16. And coming to the second question, the computer employs RAM chips of 256 by 8 and ROM chips of 1024 by 8. The computer system needs 2 kilobytes of RAM, 4 kilobytes of ROM, and 4 interface units, each with 4 registers. A memory mapped I/O configuration is used. So here, a memory mapped I/O we are using. The 2 high order bits of the address bus are assigned 00 for RAM, 01 for ROM, 10 for interface registers. Okay, so using the higher order 2 bits, we are able to differentiate the RAM, ROM, and the IO interface registers. Okay, so how many RAM and ROM chips are needed? So how many RAM and ROM chips are needed for 2 kilobytes of RAM and 4 kilobytes of ROM? Okay, so first one is see. So the available RAM chip size is 256 by 8. 256 by 8. So the required memory size is 2 kilobytes. 2 kilobytes. So 1 kilo means 1024 bytes. So that means 2 into 1024 into bits. So 1 byte is equal to 8 bits. So these are in bits. These are the bits. So the total number of chips required is equal to required memory size by the available RAM chip size. So that is equal to 2 into 1024 by into 8 by 256 into 8. So it gives 8. So that means 8 256 by 256 by 8 chips are required to for the memory size of 2 kilobytes. 2 kilobytes. Okay. So total the number of RAM chips required are 8. And coming to the ROM chip. So the size of the ROM chip is 1024 by 8. 1024. So the required memory size is equal to 4 kilobytes. So 4 kilobyte means 4 into 1 kilobyte means 1024 bytes. 1 kilobyte means 1024 bytes. So if you convert into bits, 1 byte is equal to 8 bits. Okay. So if you solve this, you will get 4. So that means the ROM, we require 4 ROM chips in order to for the memory size of the 4K 4 kilobytes, because every chip size is 1024 by 8 bits. 1024 by 8 bytes. Okay. So the total number of RAMs required are the 8 and the total ROM chips required are the 4. And second one is draw a memory map, memory address map for the system. So we need to draw the memory address mapping. Okay. So see here. So this is a component address and these are the address lines. So these are the address lines. Address lines. Okay. So first one is a RAM. First one is a RAM. So total we have 8 RAM chips. 8 RAM chips. Okay. So the size of the every RAM chip is 256 by 8. So RAM chip is size is 256 by 8. Okay, 256 by 8. So that means in order to access 256 memory locations, we require 8 address lines. 8 address lines. So using these 8 address lines, we can access 256 memory locations. So see here. So these are the representation. So 4, 4, 8 address lines. So that means for every RAM chip, the starting address will be all zeros and ending address will be all ones. Okay. And coming to the 9, 9, 10, 11. So these address lines 9, 10, 11 that can be used to for decoding purpose, because total we have 8 RAM chips. So that means RAM 1, RAM 1, RAM 2, 3, 4, 5, 6, 7, 8. So total we have 8 RAM chips. In order to select that, we require this 9, 10, 11 address lines. So these 3 address lines are required. So that means when 9, 10, 11 or 0, 0, 0, then the RAM 1 will be selected. When the 9, 10, 11, so that means 0, 0, 1, the RAM 2 will be selected. So if all these 3 address lines are 1, 1, 1, then RAM 8 will be selected. So in this way, we can select any one of the RAM. So based on this address lines 9, 10, 11. So this 9, 10, 11 are the inputs to the 3 by 8 decoder. So the outputs of the 3 by 8 decoder are connected to the respective RAM chips. And the RAM is identified with higher order 2 bits. So 0, 0. So 0, 0 is the for the RAM. So 0, 0. So 0, 0. So 0, 1 is for RAM. 1, 0 for interface. Okay. So this is a mapping. And coming to the ROM chip. So ROM chip means total we require 4 ROM chips. 4 ROM chips. So ROM 1, ROM 2, ROM 3, ROM 4. Okay. So the size of the ROM is the size of the ROM is 1024 by 8. So in order to access 1024, we require 10 address lines. We require 10 address lines. So that's why, so 1 to 4, 5 to 8, 9, 10. So these are the address lines required for the ROM. Okay. And remaining, okay, so up to 10, 1 to 10 are used for as address lines for the ROM chips, and 11, 12. So 11, 12. 11, 12 can be used as a inputs to the decoder. Inputs to the decoder. Because we have total 4 ROM chips. In order to decode, we are using this 11 and 12. So if 11 and 12 bits are 0, 0, ROM 1 will be selected. If 0, 1, ROM 2, 1, 0, ROM 3, and 1, 1, ROM 4 will be selected. So in this way, we can select any one of the ROM chip by using the 11 and 12 address lines. And 0, 1 is for differentiating the ROM, and 1, 0 for the interface. Okay, so here we have 4 interface registers. So for 1 to 4 we are using for the interface. Okay, so this is a memory address mapping of the system. And coming to the give the address range in hexadecimal for RAM, ROM, and interface. So total we have 8 RAM chips and 4 ROM chips and 4 interface registers. So these 8 RAM chips are RAM 1, 2, 3, 4, 5, 6, 7, 8. So we need to find the address range in hexadecimal for every RAM. So how we can find the address range? Suppose if you consider the RAM 1. So if you consider RAM 1, okay. So addresses are A1, A2, A3, A4, A5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these are the address lines. So for accessing the RAM 1, so what is the size of the RAM? The size of the RAM is 256. 256 by 8. 256 by 8. So that means for this, it requires 8 address lines. 8 address lines. So first we are taking RAM 1. Okay, so it requires 8 address lines. So these are the 8 address lines. So for this RAM 1, the starting address, for getting the starting address, you have to consider all address lines are 0. For ending address, all address lines will be logic 1. So 0, 0, 0, 0, 0, 0, 0, 0. So this is a starting address. This is a starting address. So next, so total we have 8 RAMs. Okay, for decoding, we are using 9, 9, 10, 11. So these 3 are we are using for the decoding. So because this is a RAM 1, so the selection lines will be 0, 0. So when the 9, 10, 11 are zeros, all zeros, then RAM 1 will be selected. So that's why zeros. And RAM, how we can differentiate the RAM from the ROM and interface, because the higher order 2 bits are used for the RAM. Okay, so higher order, that means 0, 0. So 0, 0. Okay, so 0, 0. So for finding the ending address, so the 8 address lines we have to take as all ones, and this will be same. Remaining bits will be same. Okay. So see here. So what is the address in the hexadecimal? So all zeros. So all zeros. Ending address. So this is corresponding to 0. This is corresponding to 0. This is corresponding to F. This is corresponding to F. So 0, 0, F, F. Okay. So see here. For RAM 1, the starting address will be 4 zeros and ending address will be 00FF. So next one is a RAM 2. So for the RAM 2, the starting address will be started with the ending address of the previous RAM. So previous RAM is ended with 00FF. So what is the next address? 0100. So it is the starting address for the RAM 2. Okay. So like that, we can calculate all these different addresses. And coming to the ROM, so ROM is already we have seen. So in this way, the ROM also we are calculating. So ROM 1 address is 1000 to 13FF. ROM 2 14000 to 17FF. ROM 3 18000 to 1BFF. ROM 4 1C00 to 1FFF. And coming to the interface 1. So interface 1 address range is for 2000 to 2003 because for the interface registers the address is starting with 8 because here so the most most upper 2 bits will be 10, so that's why it will be the number will be 8. Okay. So this is a interface 2, interface 3, interface 4. Okay. So here it will be 8. You will get 8 because here the interface for interface the 15 and 16 bits will be 10. So it is a 8. Okay. So for interface 4, the address range will be 800C to 800F. Okay. So in this way, we can calculate the address range in the hexadecimal. Okay. So a microprocessor can support a maximum memory of 4 GB, where the memory is word accessible. Okay. So that means the microprocessor it can support maximum of 4 gigabytes, but the memory is a word accessible. So one word is equal to 2 bytes here. So the size of the address bus of the processor at least the dash bits. So for accessing the memory as word, what should be the size of the address bus at least? So the maximum memory is the 4 GB. So maximum memory is the 4 GB. So if you convert into the bytes, 4 GB means we can write 2 power 2 into 2 power 30 because 2 power 30 means that is equal to 1 gigabyte and 2 power 2 means 4. So 4 gigabyte. So we can write to 2 power 32. So 2 power 32 bytes. That means 32, 32 address lines are required for accessing the 4 GB. Okay, so a word is equal to 2 bytes because the memory is word accessible. So one word means 2 memory locations, 2 bytes. Maximum memory is equal to the number of addresses into the number of bytes per address. So what is the maximum memory? So maximum memory is the 2 power 32 is equal to number of addresses A into the number of bytes per address. So for every address, it is occupying 2 bytes. So that's why 2. So that is equal to A is equal to 2 power 31. 2 power 31. So the size of the address bus of the processor is at least to 31 bits so that we can access up to the 4 GB. Next one, consider a 64-bit processor which supports 256 KB memory space. Processor is enhanced with word addressable memory. How many address pins are saved in enhanced processor to refer the memory? So consider a 64-bit processor. It is a 64-bit processor. That means the word length is 64 bits. So which supports 256 kilobytes memory space. Okay. So In order to access 256 kilobytes of the memory, we require 18 address lines. Because if you take log of 256, then you will get the number of address lines. So that means without memory enhancement, we require 18 address lines for accessing the 256 kilobytes of the memory. Okay. So here in the problem they mentioned the processor is enhanced with a word addressable memory. So processor is enhanced with a word addressable memory. 64 bits is treated as one cell. So we need to use 8 cells of 8 bits. So 256 kilobytes we are converting into the bytes by 8. So that means 32 kilobytes. So that is equal to 2 power 15. So that means 15 address lines are required to access 32 kilobytes of memory. So this is a with enhancer. So the number of address pins saved. So the number of address pins saved is equal to number of address pins without enhancement minus the number of address lines with enhancement. So that is equal to, so 18 is the number of address lines without enhancement and 15 are the address lines with the memory enhancement. So 18 minus 15, that is equal to 3. So by using the memory enhancement, so 3 address lines are saved. Okay. So in this lecture, we have discussed about the basics of the buses and memory transfer, and also we have solved some problems on this topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.